This video lecture is on the fundamental theorem of calculus. Now, the first thing they're showing you here is a little box explaining antidifferentiation, or what I've called before in other videos, indefinite integration, and now definite integration, where it's telling you the indefinite yields a family of functions with the plus c, and the definite integral is going to yield a numerical example with one exception, the second fundamental theorem of calculus, but the regular fundamental theorem of calculus will yield a number. And now they're explaining Leibniz, who along with Newton kind of sort of co-founded calculus kind of independently of each other. You know, Newton probably gets more credit because he's more famous. So this integration symbol is actually a modified looking S as much as anything else, not really a Greek letter or anything like that. Alrighty, now the fundamental theorem of calculus says to evaluate a to b f of x dx is big F, which big F, we've talked about this in the another video. Big F is the antiderivative of little f, so you're finding the antiderivative function. So you take the big F, plug in b, take the big F, plug in a, subtract. Now when I work problems, what you'll see me do, you see that the way I do these is, you know, and this is common notation, is you write the antiderivative function, and then you put this vertical line. That vertical line with b and a, that's just like a holding position. In other words, you found the antiderivative. It means once you find the antiderivative, the integral symbol is gone and the dx is gone. Same time. And you have a vertical line with b and a, meaning now you're about to plug in the b, plug in the a, and then subtract. Now I'm going to go back to another lecture video, this problem. Now I don't have a tablet PC I'm working with right now, but that's okay. This one's simple enough that I can explain it without it. You know, I showed this process of using the Riemann sums and the limit and all that kind of business. Well, to evaluate it using that rule I just showed you, the antiderivative of 2x would be x squared. I think that makes sense, right? Because the derivative of x squared is 2x. So if you write down x squared, then you plug in 1 and you plug in negative 2, what would happen? 1 squared would be 1. Negative 2 squared would be 4. 1 minus 4 would equal negative 3. And look what we have right down there. Negative 3. Wow. See? I told you it was going to be much easier doing it with this formula than it was that way. But I can appreciate the beauty of the theorem that creates it. So yeah, we don't want to do it that long-winded way ever, really. Now here's, so I start putting some of these in Maple. You can do these in the graphing calculator. This is similar to one I talked about earlier. Notice that there's a discontinuity at 0 between negative 2 and 3. So even if the answer did produce something, and it would if you worked it out manually. I think I did that. No, I didn't. Yeah, no. But if you did the antiderivative and plugged in those two numbers, you'd get a result, but that result is wrong. It was wrong to have ever done it. So Maple just spits out infinity. The calculator gives you some sort of, you know, game over here. It didn't do it, which is good. It didn't. Here it shows error. Now I have a TI-84C. When I first created these notes a while back, if you're using an old 83 with an older operating system, maybe even an 84, you have to use this. It's still the same function f and n, but you have to write it this way. You write your function, you tell us the variable x, put the lower limit, put the upper limit. With the newer ones, it will spit, f and n will just spit out the integral with like empty boxes there, and you put the number, and you just put the numbers in, more in a way that you would write it out, more looks kind of more like how you put it in an integral, and it gave an error here. So yeah, so if hey, you're looking at this problem up here and going, my calculator doesn't look like it would do f and n. That's because yours is a little more modern. Now, let's say you wanted to evaluate this from 1 to 3. 1 to 3 would be acceptable because 0 is not in that interval. There's no discontinuities for 1 over x squared from 1 to 3. So now we'll refer back to the antiderivative process to find using this formula that we saw in the first section, our beloved power rule there. Remember that. X to the n plus 1 over n plus 1 as long as n is not negative 1. So you bring the x squared up, because we talked about that you can't apply the power rule in the denominator. So it makes it x to the negative 2. So which is negative 2 plus 1 is negative 1. And then when you divide by negative 1, that's just the same thing as just having a negative sign out here. Same thing as dividing by negative 1. Now, to evaluate this, I rewrote it then back as 1 over x. Made it negative 1 over x. Now this goes back, this next step goes back to a property from the previous section's integral using definite integral property, where if you want to do this, you don't have to, but you still should be familiar with the property though, that I flipped these limits of integration like so, which created that negative sign. And my goal for creating that negative sign was to get rid of that negative sign. So the negatives cancel. Now I have 1 on top, 3 on bottom. So this means we've taken the antiderivative. Oh, I forgot to mention up here, Stewie says there, do not add plus c. Definite integrals do not have plus c in their answer. All right, so you put now, this is like a holding position. It means, okay, you've got the antiderivative. Now you're about to plug in the numbers. Put in 1, 1 over 1 is 1. 3, 1 over 3 is 1/3. And you get 2/3. Which, there it is in the graphing calculator. And I converted to fraction, which is 2/3. And I used the Maple software. Put it in there and got 2/3. So I'm feeling pretty good about 2/3. And I'd mentioned this in the previous video, but that's certainly good to have this in here again. So the value for any definite integral can be any real number, positive, negative, or 0. But if the definite integral is supposed to find area, the answer must be positive. And this is the same problem from another video, the same function, where at the time I just showed you that this was the integral that would evaluate the area right here. But now we have the ability, to find the integral, because we now know the rule. So there it is. If you want to do it in the calculator, that's fine. You get 74 over 3, but if you're doing it, if you're just using a regular scientific calculator, it's not too bad. It's not too difficult to do it by hand. But so the antiderivative using the power rule, x squared would be 1/3 x cubed. And for 3x would be 3x squared over 2. And the antiderivative of 2 is 2x. All right, now, so I got the 3 and the 1. Means it's in the holding position, about to get plugged in. So I put in 3 into this part right over here. I won't go through the verbal part of saying each one of these. 3 went in each one of those and got those 3 results. Put in 1 into this parentheses to get these 3 numbers. And then just kind of did a little arithmetic. That's all this is arithmetic. 9 plus 6 minus 2 is 13. I combine the integers. Then it turns out 27 over 2 minus 3 over 2 is an integer because it's 24 over 2, which is 12. And you end up with that minus 1/3. Common denominator, simple arithmetic, 74 over 3. And this is just, you can look at this. This is basically what we've been doing. They sort of show that the C's actually kind of cancel each other out, but yeah, you don't ever need to write them in the problem. There's going to be no C at the end. So this is just kind of summarizing. I just took it out of the book so you could sort of see it, summarizing the process. Their line, they don't have like a vertical line. They have some weird little thing like that. But, so either way is okay. You just don't put the integral symbol back in there. That's the important part. So here's another one. The integral of 4x cubed minus 3x squared from 1 to 3. Take the antiderivative. X to the 3 plus 1 is 4 divided by 4, which will make those 4's cancel. X squared plus 1. 2 plus 1 is 3. Divided by 3 means the 3's cancel. So there's my bar, 1 to 3. So I put in 3. So it's 3 to the 4th minus 3 cubed. Minus, that's always minus right there between the two parentheses. Always, by definition, right there. And 1 to the 4th minus 1 cubed. 81 minus 27 minus that 0 right there. We get 54 for that definite integral. And once again, there's the maple on the right, but if you used a more modern calculator and did the infinite, it will actually show you an integral sign where you put the numbers in there. Let's see if I have any. I had that one earlier, but let's see if I. Well, there's another one coming up where it shows it with the newer one. Okay. Now here's another one with kind of weird looking, but remember there's no quotient rule, so you have to divide it up term by term. So just using properties of exponents, there's just one of them's a fraction on the bottom. So I just pulled that 2 out, and the denominator made it 1/2. So it's x divided by the cube root of x, which is x to the 1/3, minus x squared divided by x to the 1/3. Okay, so just subtract the exponents. 1 minus 1/3 is 2/3. 2 minus 1/3 is 5/3. So we haven't integrated anything yet. That's just the simplification process. Now we're ready to. So you see, I'm about to do the antiderivative, so my integral sign is going to go, and my dx is going to go at the same time. Those both go away at the same time. So power rule, 2/3 plus 1 is 5/3. So when you divide by 5/3, that makes it a 3/2. Same thing here. 5/3 plus 1 is 8/3. That'll put a 3/8 in front. From -8 to -1, we still have that 1/2 we can't forget about in the front. And I'm not going to go through all the arithmetic here, but I figure you can use a better way in the calculator to do it. I'll show you what I did here. I distributed the 1/2 through the parentheses. One way I did it was I put the antiderivative function right here and used the vars, y vars function and just plugged in negative. So this -1 minus -8, that means I put it into the antiderivative. In other words, y1 is not your original function in this case. It's the antiderivative. And there's the f and it. Comes up to be the same thing. There's the more modern version of the calculator. And I'm sure if I put it in maple, it would also be, oh, there, I mentioned it right there. Okay, good. Same thing. That was a little messy, but, you know, with the use of calculator, it's not too bad. Yeah, the convenient thing about this one is that even though it has fractional exponents, you know, those thirds mean cube roots. The cube root of -1 is a whole number, and the cube root of -8 is a whole number. So that made the calculation. We didn't have a bunch of radicals in the answer. Alrighty. All right, find the area of the region. So look at number 36. You see it's 1 over x squared from the region 1 to 2. And it satisfies the criteria that we have right now. The graph must be Non-negative means either above or touching the x-axis. I mentioned in another video that graphs that dip below the axis or two different graphs, stuff like that, all that is taken care of in the Cal 2 part of our course, our calculus sequence. Some calculus sequence, they have it in their Cal 1. At Lone Star, we do not. So there's just wrote that as -2. So we've used this particular function before. I used it earlier, like it was just from 1 to 3, the same problem. -x and -1, so we saw this earlier, and I didn't write the negative sign here, but you see I wrote the red 1, so that switching the 1 and the 2 created the negative that kills this negative right there. So now all negatives are gone. So we put in 1 there, makes it 1 over 1 is 1, 2, 1 over 2 is 1/2. 1 minus 1/2 is 1/2. Absolute value functions. To integrate absolute value functions, sort of long-handed by properly setting up the integral. Because technically an absolute value function is really, it's a piecewise function, as I have written over here, of two different lines. Now, of course, if it's the absolute value of x minus 2, these will be x minus 2's here. But it's actually two separate functions, and they intersect right there. So you have to actually treat it as two separate pieces. You can't do this straight from A to B. Assuming that assuming that where the point is between A and B. If the point's not between A and B, then you can do it as one process. So what you have to do is you have to find that value where the graph changes direction, the form of the point. Now this one's obvious to see that it's 0, and the way you do this is that, so in this case, see I wrote x minus c. So if the absolute value function was x minus 2, 2 would be the point where it separates. So it's always just whatever makes that 0. Obviously, if it's just x, 0 makes it 0. So you treat this as two lines, one with a negative slope, one with a positive slope, and go from there. And you see I have, so here's kind of the setup. So it'd go from A to C with the negative of it, of the function, you drop the absolute value, and then from C to B, C is the value, so where the graph changes direction. Clean that up for a sec. And then we evaluate the two definite integrals separately and add them together. And all right, so there's an example I have right below. Is from 0 to 7 of 3x minus 5 dx, absolute value. So right over here in blue, I did the 3x minus 5, and to find the point where the v changes, and it's 5/3, which is obviously between 0 and 7. I graphed it just for the heck of it. So the process goes like this. It'll be from 0 to 5/3, because the point where it separates, the negative of 3x minus 5, plus the rest of the way 5/3 to 7 of the positive part of it right there. So basically at this point, once you get it set up, you work those two definite integrals separately and add them together, and that will be the result. And what I did here, I used my little negative trick there by flipping them, and flipped the limits over, and the negative killed that negative. So I have the same antiderivative in both cases here. So antiderivative of 3x would be 3/2 x squared minus 5x. We have 0 5/3. Same antiderivative, 7 and 5/3. You can use a calculator to plug all this in. There's the F and N. I worked it out old school here. I might have used a calculator for part of that, obviously, but I got 281 over 6. So I set it up in the old F and N way where I added them together. On the right, here's the newer version of it, where you actually see the integrals. And I got 281 over 6 every way I did it, so I feel pretty good about it. And also I just used a y-bars technique there or whatever, which is not necessary. Another way that this problem could be done also is if you found the area of those two triangles and added them together. That would also work. But it's fun to, I think, to look at the calculus way, I guess. I don't know. It is for me. Here's some more definite integrals. Now we're bringing in some trig functions, which we've seen the antiderivatives. So 2 plus cos x dx from 0 to pi. The antiderivative of 2 would be 2x. Antiderivative of cosine would be positive sine. Now be careful with that. It's got to get used to that, because you're used to the derivative of cosine being negative sine, but the antiderivative of cosine is positive sine. If you think about it, if this is antiderivative, the derivative of that sine right there is cosine. Pi and 0, so you end up 2 pi, sine of pi is 0, 0 makes all that 0. Be careful, because 0 doesn't make cosine 0, just makes sine 0. And you get 2 pi. Here's another one. So this is important to know that the antiderivative of negative cosecant squared would be positive cotangent, because the derivative of cotangent is negative cosecant squared. So once we have 2x plus cotangent x, we plug in those values and plug them in. So 2 times pi over 2 will be pi. Cotangent's cosine over sine. That's going to be 0, because cosine of pi over 2 is 0. Sine of pi over 2 is 1. Pi over 4 makes that pi over 2. Cotangent of pi over 4 is actually 1. And you got a minus between them, and we end up with pi over 2 minus 1. All right, now we have something called the mean value theorem for integrals. Yes, we had a mean value theorem for derivatives at a point in time. So now let's have one for integrals. So if continuous in a closed interval a to b, then there exists a number c in a to b where the definite integral will equal f of c times b minus a. All right, now we're going to kind of expand the mean value theorem into what's called this average value. It's going to be a manipulation of this theorem to help us find what's called the average value. Keep everything on the screen here. Suppose you want to find the average value of a function on an interval, continuous. So you think average, you think your basic arithmetic average, where you add up all your numbers and divide by how many of them you have. Well, you cannot do that for a continuous function, because continuous function has infinite values. Even if you're like on the interval from 2 to 4, you have infinite values on that 2 to 4. That's why we have interval notation to represent all real numbers. So it would be impossible to figure out the average of every y value between 2 and 4. But the integral allows us to do it. So what we have here, the average value of a function on the interval does relate up here to the mean value theorem. If you divide both sides by b minus a, this f of c actually is the same thing as the average value. So the average value is basically the definite integral divided by b minus a, or the way I wrote it, 1 over b minus a, same thing. And then what we're trying to do is we're trying to find the value. The theorem guarantees you're going to have a c value that equals this average value. So when I divide by b minus a, I have an average value, and I want to find the c that equals that average value. You're guaranteed to have at least one. Now this picture is strictly a rough, or it could have more than one, rough approximation. I have no way to verify that's the average value of all those y values, but it looks reasonable. So imagine if you were, adding all those, some of them are below, some of them are above, some are below. I just drew a horizontal line representing the average value. And in this particular instance, if that was correct or close to correct, we'd have two values in this graph in the interval a to b, where the function value, the y value, equal that average value, meaning the average value as a horizontal line crosses that curve. So let's try this out. It's not a bad calculation. Same thing here. Okay, so we're using the mean value of theorem for integrals. That's what guarantees all this, but we're actually finding the average value, and then we're going to find the value c where it equals that average value. All right, well, I'll kind of speed up through the details on this part of it, the next part of it, because this is pretty basic, definite integral. I'm sure you can do it. -3, x to the -2 over -2, 9 halves, 3 in the 1, makes that -9/4. Plug in 3, gives you 1 over 9. Plug in 1, gives you 1. Now this one, for some reason, I could have chosen to flip those limits of integration and use the negative to kill that negative. For some reason I decided not to this time. But like I said, it wasn't mandatory either way, so you work this out and you should get 2. So that means for the function, there it is, that weird curve 9, for 9 over x cubed from 1 to 3, well the 1's way up here, but there. I should just put the dots here, that'll make it a little easier. So for every y value, where that's going to hit that curve up there fairly soon, but well, it's going to be at 9, obviously, because when y equals 9 over x cubed, when x is 1, y is 9. So your first y value is 9, and your last y value at 3 is 9 over 27. 3 cubed is 27, just above 0. So all those y values between 9 and 1 over 27 will average out to be 2, according to the average value, which comes from the mean value theorem. So the average value is 2. And what we do here is then we take our function, 9 over x cubed. It's not critical that you change it to c, but I like to, just for the fun of it. Now, so you just take this function 9, so 9 over, put a c cubed equals 2, that average value from up here. Solve it, so I'll multiply both sides, got 2c cubed equals 9, c cubed equals 9 halves, so technically the exact answer would be the cube root of 9 halves. Yeah, no one said this had to be a pretty answer, but if you take your calculator and calculate the cube root of 9 halves, cube root of 4.5, it's going to be 1 point something. Well, 1 point something is between 1 and 3. So according to the theorem, we got at least one value that we're supposed to. Because if it satisfies all the conditions, that means if you didn't get one, that means you did something wrong. So I graphed the curve, and I graphed the horizontal line y equals 2, representing the average value. So you see that point where they meet, where the red and blue cross each other, if you drag that down right about whatever that is, that dot, 1 point whatever, that will be the cube root of 4.5. So it worked. All right, here's another one where we're going to find the average value. So we're going to evaluate. Okay, so it's 1 over b minus a. Not sure if I remember to mention that up here. I have it written, but yeah, 1 over 3 minus 1. So it's 1 over 1 minus 0. And then the antiderivative of 0 to 1 of 4x cubed minus 3x squared, and which will give me pretty easy antiderivative. That's going to be x to the fourth minus x cubed. All right. And plug in 1, plug in 0, and you work that out, and you get 0. That's okay. Yeah, no rule says the average value can't be 0. That means the average of all y values on this interval from 0 to 1 of the blue graph, which is hitting at 0, it's coming down below a little bit. So obviously if some of them are negative, you better have some positives in there if it's going to be 0. And you see there are some positive values right there at the end. But the average of all those is 0. Every real number in there. So basically, we set the derivative equal to 0. And I put the c in there, so remember we're going back to the original function, remember, not the antiderivative. So put in 4c cubed minus 3c squared equals 0. Factor out of c squared, leaves you 4c minus 3. C squared equals 0 means c equals 0. 4c minus 3 equals 0. C equals 3/4. I try to avoid endpoints being the answer in my problems, but that's okay. But well, yeah, we'll include that endpoint in this case. That's fine. So 0, but then 3/4 is the other location right over there. So the red line represents y equals 0, the average value being 0. So we'll say right there is the 3/4, and then there's the 0. All right. Now this one I thought kind of interesting to look at. I generally don't ask this one for test purposes, but it's good to have, trig skills are always good, understanding trig functions. Okay, working out the average value for this is not difficult. And that was really not difficult at all, as long as you understand inverse trig functions from back in trig and pre-calc. So I take 1 over pi over 2 minus 0, and then the integral from 0 to pi over 2 of cos x dx. So that's easy enough. That integral is just sine x, 2 over pi, and 0 to pi over 2. Plug that in. Sine of pi over 2 is 1. Sine of 0 is 0. 2. So you get 2 over pi. So the average value is 2 over pi. All right. Now to find the point for this one is in radians. We're doing this in radians, not degrees. So you're trying to find where cosine c equals 2 over pi. Well, to get c, you have to use the inverse function. Cosine inverse of 2 over pi is 0.88 radians. Now I'm going to try to draw something here, or maybe it'd be easier if I just copy the unit circle into this discussion, but this picture doesn't have to be perfect. Well, actually, I can make it a circle real easy like this. Okay. All right. Well, and that's when solving trig equations can be difficult for students sometimes. It's these inverses. Technically, vertical line right there. Okay, here. The cosine inverse is only defined from 0 to pi, so point and cosine is positive in quadrants 1 and 4. So you figure, let's see, pi over 2 is about 1.47 radians. I'm going to give it a color here. 1.57 radians. That's up here. I don't know, so I'll put 0.88 right over there. But it's kind of interesting is that if you're just solving the equation, like for example, cosine of x equals 2 over pi, there are actually two answers. See, the inverse function of the calculator only gives you one answer, but there's actually one down here too, where it's also positive. But we don't care about that answer, but mathematically there are two. Okay, so I just thought I'd mention that real quick. I'm just going to give you a quick verbal example. Let's say you're solving the equation sine of x equals 1/2. If you do the inverse function, if you do it in degrees, it'll give you 30 degrees, which you can then convert to pi over 6 radians. It's only going to give you one of the answer. But technically, if you're solving the equation sine of x equals 1/2, there are two answers, pi over 6 and 5 pi over 6. That's what I was trying to get at with this. But for this case, it's not necessary because we know we're between 0 and pi over 2, so there's not another answer that needs to be included here. So we won't have to worry about that. So anyway, so I graphed this was an older calculator. I should redo this with the colorful graphs. There's 2 over pi, and there's the graph, and this 0.88 right there. See, that's where the 2 over pi intersects the curve at 0.88 radians. That answer right there. That's kind of a problem. I might do the average value on the test, but no, I'm not likely to ask this one. But I mean, trig functions, it's good to be comfortable with them and not fear them. The definite integral as a function of x, which is going to lead to a new theorem. Now, yeah, there's a whole subject on just integral functions. You can find a whole book on that. But I'm using big F of x to define this integral function where you see that's not x right here. It's cosine of t dt, but because we have an x in our limit of integration, that will make the result be variable x. So this one, you take the antiderivative of cos of t dt will be sine of t. And now I drew the bar, put in the x, put in the pi over 2. So sine of, put in t for x, you get sine of x, put in pi over 2, you get minus 1. So so you see that f of x here ultimately, even though it's written as an integral with t's, ultimately it is variable x at the end. All right. Now, and this will come up. I'm showing you this. Let's take the derivative of big F. So with sine x minus 1, derivative of big F would be cos x. We'll talk about why this is important here in a minute. Let's look at the next one. 0 to x squared, cos of t dt, the antiderivative of sine of t. Put in x squared, put in 0. So it's sine of x squared minus sine of 0, sine of 0 is 0. So the integral function then, g of x, would equal sine of x squared. Now suppose I want to take the derivative of that. So we must not forget our friend the chain rule. The derivative of sine of x squared will be cos of x squared, also with the derivative of x squared attached to it, all from the chain rule. I just put the 2x in front because I like the way it looks better. But even though I wrote it at the end, I put it in the front. Now Maple kind of did it weird. I don't know why they put the 2 in the front and the x at the end. Whatever, that's okay. That's fine. So that's the derivative of it would be 2x cosine of x squared. The second fundamental theorem of calculus. All right, f is continuous in an open interval I containing c. Then for every x in the interval, the derivative of this integral, if you have just some constant here and x on top, will just be f of x. Literally, you replace t with x, and that's it. Over here, the derivative of the integral. For this one, if it's g of x, meaning it's a function of x, like x squared or something like that, like we just did a minute ago. You put the x squared in for the t, like so, and then you take the derivative of that x squared, or whatever it is, of that g prime of x. So if it was x squared, it'd be 2x. So it's basically finding the derivative of the integral. Now, you might think, well, why don't we just do what you did up here? Work the integral out and then take its derivative and get the answer like this. Same thing here. Well, that would be fine and dandy if the function can be integrated. What we're going to use this theorem for is that we're going to see that we can get the derivative of that integral function without actually integrating the function. And that's what this, once you see that it's done, this is something that if you catch it, it'll take about 2 seconds to do the problem. It's super easy to work it out. But, I have like mixed results when I have handwritten tests. A lot of people just nail it, no problem. Some people have no clue because they try to overcomplicate it. It's not as complicated as it may appear. I mean, like I said, literally, if this is x and you're trying to find the derivative of this, you literally just put x in for the t, and that's the answer. There was no derivative. Now, there's a derivative involved. There was no integral involved whatsoever because the derivative is offsetting the integral. Same thing here. All you're doing is putting the g of x in there and then multiplying it by the derivative. So people make this really, really, really more difficult than needs be. Now, there is a way in Cal 2 to integrate secant cubed. It's very complicated. And for this kind of problem, even if you knew how to integrate it, you darn sure don't want to because this is super simple. But look how easy this is. So it's defining f of x as this integral function. So it's not saying, it's not asking for us to figure out what f of x is. I think that might be the confusing part. It just wants the derivative of f of x without even knowing what f of x is. And that's perfect. That makes it so simple. So literally, because we have an x up here and a number down there, it could be 0 or any other number, all you do is put the x in for the t, and the answer is just secant cubed of x. That was literally it. But notice you see how that says f prime of x. By doing that, we are finding the derivative. We're not finding what f of x equals. We're finding what the derivative equals. Super easy. Don't make this too complicated. Next one. No difference, no problem with the 1 being down there because it's just still a constant. It's x again. So all you do is come over here to where the t's are, put an x everywhere you see a t. So it'll be t squared becomes x squared, t squared plus 1 becomes x squared plus 1. How about that? All right, now, a little interesting. This is using the other part of the rule. Not that much more worse. It's x squared now, so it's not just x. So what we do is two things. We put the x squared in for the theta, right here. And then we take the derivative of x squared and attach it at the end. Or, well, end beginning, just attach it to the answer. I just rewrote it. So you put x squared in, but you still have the square right there, the exponent for the theta. So it's x squared goes in for theta, so it's x squared squared, and then the 2x represents the derivative of x squared. So it's 2x sine of x to the 4th, x squared squared, and that's it. Yeah, so for that one, you have to remember the derivative of the exponent. How about this one? All right, secant x and a 4, square root of t cubed plus 1. We're not integrating anything to find this derivative. All we do is put the sec cubed in for the t. So part of the answer will be the square root of sec cubed plus 1. That's part of it. Then we need to attach the derivative of the secant. So obviously you need to know what the derivative of the secant. And then so it would be the square root of sec cubed plus 1 times the derivative of secant, which is sec 10. And Bucky approves of that answer. You see I use different symbols sometimes to represent the answer. Check marks, UH logos, because that's where I'm the alumnus from. And I just started using Bucky's. I had a student who wore Bucky t-shirts a lot, so let's put Bucky in there. So Bucky gives his approval. Now this one, if you have variables top and bottom, you do them separately and subtract. So it's not that big a deal. Just subtract the answers. So for this one, once again, the derivative, no integrating involved here. Put x cubed in for t, so you have cos of x cubed, times the derivative of that, which will be 3x squared, minus put x squared in for t, which will be cos of x squared, times the derivative of x squared, which is 2x. And so we subtract, and Bucky approves of that one. The net change theorem. The definite integral of the rate of change of some quantity, f prime of x, gives you the total change, or what's called the net change from A to B. Meaning, if you know at what rate something is changing. Remember, rate, we learned way back when, is derivative, right? Rate of change is a derivative. So this is just saying you're integrating the derivative to figure out what the actual amount or whatever it is changing, or whatever. So it's really not that complicated. It's actually pretty easy, you know. So it gives you a rate of change. So this problem says, so all you're doing is taking the antiderivative from A to B. That's all you do. So the water's flowing out of a tank at a rate of 500 minus 5t liters per minute. That's the rate of change. Find the amount of water that flows out of the tank during the first 18 minutes. So the first 18 minutes means from time 0. So it's from 0 to 18 of that function, 500 minus 5t. Okay, you can work this out with the f and it if you want to. That's fine. Do it with the antiderivative. I think once we set this up, by now you should be skilled enough to evaluate that, no problem. Super easy. I'm not picky about units that much, like they would be in a science or engineering class, or as well they should be, but it would be liters, because it's liters per minute. So 8,190 liters is the actual amount that comes out of there if it's flowing at 500 minus 5t liters per minute. All right, flowing water, leaking oil. All right, 1 p.m. So 1 p.m. you have to keep in mind that's our time 0 in this case. So that's trying to get sneaky on us there. So it gives us our rate, you know, so it's leaking from a tank at a rate of 4 plus 0.75t gallons per hour. How much oil is lost from 1 p.m. to 4 p.m. So that's what we have to realize here, is that 1 p.m. is 0, and then 4 p.m. is 3 hours after 1 p.m. So it's 0 to 3, not 1 to 4. I can see how somebody might make that mistake. Had it said noon, you know, if it said start at noon, then 1 to 4 would have been correct. All right, antiderivative of 4 will be 4t, 0.75t will be 0.75t squared over 2. Plug in 3, plug in 0. We get 8.75 gallons. We'll give it the flag of approval. So there you go. This isn't too bad. So the next one's going to be, what's that going to be? From 4 to 7 means you're starting at time 3 and you're going to time 6. So it changes the limits of integration from 3 to 6. And okay, same antiderivative, blah, blah, blah. Plug in 6, plug in 3, and you get 1.875 gallons from 3 to 6. So you can see that, you know, even though they're both 3-hour time periods, the rate, you know, more of it's lost in the first 3 hours than the second 3 hours, because it's just not coming in and slows down how much it comes out. So, and that concludes this video lecture.